So first we'll be hearing from Kim Nitu Rai, who will be talking about simulation of intensity interferometry for binary star systems. So please take it away.
Thank you. Okay. Hello, everyone. I am Nitu Rai. I'm going to discuss my work, which is simulation of intensity interferometry for binary star system. This work has been done in collaboration with Professor Prasenjit Saha, Professor Subrata Sarangi, and Professor Somen Basak. As we all know, the intensity interferometry was first introduced by Hanbury, Brown, and Twist in 1954 to measure the angular radii of stars, and they successfully measured it also for 32 stars, including Spica. But in lack of high sensitive photon correlator and computing techniques, it was stopped soon. But now, when these techniques have made a lot of progress in their field, this intensity interferometry is much more efficient. You have seen in David Kida poster also, they have measured single, binary, and multiple stars using VSII. And next up, you will also see that. So we have taken a closed binary star system like Spica. Habitable have already measured the radii of one star together with the masses of both stars, but they couldn't measure the radii of the other star. So here we are going to estimate the both radii of stars together with their limb darkening coefficients and the astrometric orbit with the combined signal, that is a squared visibility signal of binary star with a sufficient value of SNR. So you can see here, we have taken three orientation of baseline with respect to the source alignment and with two different frequency. Also, we have considered that the less informative part of the UV plane have been removed and with total number of observed SNR value 208, we have estimated the angular radii of star A with uncertainty 2.06 micro arc second and angular radii of star B with 4.12 micro arc second uncertainty. Also, we have estimated the astrometric orbit of this binary system with 8.25 micro arc second uncertainty. Not only these three parameters, even when we assume the model, the limb darkening model of stars with assumption that the limb darkening model is following the sum of linear, this quadratic and cubic model, we have estimated the linear limb darkening coefficient also together with the other three parameters. The total SNR value of this instrument was here 1850. However, we couldn't estimate the quadratic coefficient and the cubic coefficient because we are considering that in our signal, the contribution of these two coefficient is very low. The good thing is that this two coefficient couldn't have been estimated, but these are not affecting the other parameters. Other parameters are easily estimated. So what about the wide binary system like Alpha Centauri? Like if we want to estimate the astrometric orbit so that we can detect the perturbation in orbit due to an exoplanet around Alpha Centauri A, which is revolving at Earth-like orbit. So we have considered here a 10 Jupiter mass to show you just the perturbation in orbit. But for our rest of work, we have taken the lower mass also. But when we started to do simulation, we faced a challenge. The challenge was that, as we know that Alpha Centauri is a wide binary system, so the interference pattern of this system was lying in a very small radii of a radius. So this fringe pattern will be washed out with finite diameter of a plane aperture. To deal with this challenge, we introduced a masked aperture, which is just a simple aperture, which is following this cosine square formula, so that there are strips on this aperture with different lengths. So this one single baseline will be result in a mini baseline. That means we can easily detect the fringes using this kind of aperture. So what will be the width and orientation of this aperture? To show the result of this, I mean answer of this question, we have simulated a signal for a baseline which is 1 meter in east and -3 meter in north. We have taken the observation only for 15 minutes for each 1 second of average time. Here you can see that as the mask widths are varying, the signal is varying, and for 22.5 millimeter of mask width, the signal is higher. Similarly, when we do the simulation for masking orientation for the same baseline and the same time of observation, we see that when the orientation is 104 degree along the U axis of the baseline, this signal is higher. So for the rest of work, we take these two value, masking with 22.5 millimeter and masking orientation 104 degree. We take 4 number of telescope which have been arranged here. The reason behind of this arrangement is just to get a good signal strength, nothing else. And also this telescope's aperture are just representing, it's not a correct 40 centimeter of diameter. So we are assuming all parameter of each telescope equal, and that means that each telescope has 40 centimeter of diameter, 2.25 centimeter of masking width, and 104 degree of orientation. We see that the signal related to each baseline is here, and also we see that the signal strength is really good. So first we take the observation for 1 night here, and we try to estimate the astrometric orbit, and we see that what is the estimation error. So estimation error was very high, which was 0.5 milliarcsecond, and which is obvious. So as we know that when we will increase the number of night of observation, this error will drop according to the square root of nights. So we take 10 number of channels and 1000 number of night of observation, and we estimate the parameters, that means the astrometric orbit of x coordinate and y coordinate here, with a total SNR value 7 into 10 to power 6, and we see that the x coordinate have been estimated with 5.3 microarcsecond, and y coordinate have been estimated with 6.2 microarcsecond. That means we can say that, yeah, if there will be a planet in Earth-like orbit, so that we can detect the perturbation with this kind of setup. To fit the orbit of the planet, we have taken 3 years of observation, and we have used the least square method and fit this signal with some of the polynomial functions, which is 6th order polynomial function, and also a oscillatory function here. We have taken this delta x bar and delta y bar is representing the just error in signal, which have been shown here in yellow color, and this blue color is representing the orbit of the planet. Using this method, we have estimated the orbit period of this planet 0.841 year, which is lesser than the orbital year which have been taken. We have taken in the beginning 1 year of the orbit, and it is because of the orbital perturbation of the binary system. Also, when we thought, okay, what will be the minimum mass of planet which can be detectable with this kind of setup, we have done the simulation here, and we see that, yeah, as the mass is decreasing, the interferometric error, which is here in green color, it's increasing. So we see that till Neptune mass planet, approximately 16 Earth masses of planet, still the perturbation is comparable. I mean, the interferometric error bar is comparable to the perturbation. Even the y coordinate error was very low than the perturbation. So we say that, yeah, till Neptune mass of planet, we will be able to estimate the astrometric orbit with this kind of setup. To show the same simulation for different orbit and with Neptune mass planet, we have done the simulation in the right one. You can see here, and we estimate the periodic year of each orbit for this Neptune mass planet. So we conclude that using this combined square visibility signal of intensity interferometry for a closed binary system, we are able to estimate together the radii and linear limb darkening coefficients of both stars and also the astrometric orbit. And when we deal with the wide binary system like Alpha Centauri, we faced a challenge with a plane aperture. So we introduced a masked aperture in front of this, and with less number of uncertainty, we are able to estimate the astrometric orbit for Neptune mass planet. At the end of this talk, I would like to thank my supervisor, Professor Soman Basak, and my collaborators, Professor Prasenjit Saha and Professor Subroto Sarangi, for their kind guidance and support. Also, I would like to thank my institute for providing me access to the Padmanabhan cluster so that I could do the high performance computing things. I would also like to thank this conference for providing me the opportunity so that I could discuss my work. Also, I would like to thank the audience to listen me, and now I would like to have questions and your suggestions, please.
Okay. Thank you for that fascinating talk, and thank you for staying within time. Do we have a question, either online or in person? None so far. If not, I can start us off. So you said that the error on your observations goes with the inverse of the square root of a number of nights.
Yes.
So how many nights would you typically be looking to observe to get the accuracy that you require?
1,000 number of nights.
Yeah,
Here
total number of nights.
Yeah, I have shown for 35 number of nights, but when I wanted to get the good uncertainty, I took 1,000 number of nights.
Okay.
Yeah.
Interesting. Any other questions? Okay, if not, we can thank the speaker again.
Thank you.